hand it over to him for his presentation. So Mr. Clark received his Bachelor of Science and Masters of Science degrees in geology from the University of Iowa. He is a licensed professional geologist and was an Iowa certified groundwater professional from 2008 to 2012. Mr. Clark previously worked as an environmental project manager for Terracon Consultants in Cedar Rapids. He joined the Iowa Geological Survey in 2012 as a bedrock geologist, focusing on geologic mapping, stratigraphy, well logging, and public engagement. So I'm going to go ahead and pass it over to Ryan to start his presentation. We are going to be doing questions at the end. So if possible, please submit your questions to the Q&A function to make it a little easier for us to go through and try and get as many questions answered.
Excellent, Tabitha. Thank you very much for the introduction and for inviting me to speak here today. As advertised, I would like to talk about the potential for geologic carbon sequestration in Iowa. This is a presentation that I've given multiple times over the last 2 or 3 years. Primarily, or I guess of note, this very similar presentation was given by myself and the state geologist Keith Schilling, my supervisor, to the Environmental Protection Commission of the Iowa legislature back in February. We've also given this presentation to the Iowa Utilities Board and various other organizations. So it's something that we've been trying to draw attention to over the last few years and gradually get more and more people interested and informed. And that's what I hope to do here today. And as Tabitha mentioned, we'll get plenty of time at the end for questions. What I'd like to talk about is introduce everybody to what carbon sequestration is, and then discuss the future, and then, of course, why does it matter in Iowa? We'll touch on the benefits and spend the geologic part, I guess, is where to search. And then I'll wrap up with how we would propose to assess this potential in Iowa. So carbon sequestration, the acronym is CCUS, and that stands for Carbon Capture, Utilization, and Storage. The carbon capture part is somewhat self-explanatory. The CO2 is emitted as a gas, and that can be captured in some cases pre-combustion or post-combustion. And then there's also direct air capture. And I've got an artist rendering of a direct air capture system here in the image, and that's something that I'm not going to be discussing today, but that is a type of carbon capture that can be utilized in a variety of scenarios. It can be placed pretty much anywhere that you have the space and the infrastructure. The utilization part, at this point, it's more or less a small piece of the pie in terms of the goals of carbon sequestration and carbon reduction, but there's a lot of research going into this aspect of it, and I feel like that'll be an emerging industry, certainly in the future. But what I'm going to focus on today is the storage aspect. So there's several different types of geologic storage, and this figure summarizes those fairly well, although it really bugs me when I see aquifers portrayed as underground rivers, because that's not what they are. And I'll discuss what an aquifer is in greater detail later on. But this figure was one of the better ones I could find to discuss. There are opportunities in terms of coal bed methane. And what coal bed methane is there is the in-place coal in the bedrock can actually absorb the CO2 molecules. But in that process, it actually kicks out methane molecules. And so even though we do have a lot of in situ coal in Iowa's bedrock formations, primarily in the south central part of the state, this is not an aspect that we're really interested in. The Department of Energy is not really interested in it because, the production of methane is something that's sort of counterproductive to the idea of carbon sequestration anyway. Really what I want to focus on are the types of geologic storage known as enhanced oil recovery. And that's where you can actually inject CO2 into depleted oil and gas reservoirs. The other one is a lot more widely utilized and studied here in the Midwest, and that's saline aquifer storage. And that's what I think we have a really big potential for. So narrowing it down to the two different, or to these three different types of geologic storage, really what it boils down to is the CO2 is emitted as a gas, and then it must be compressed and dehydrated into what's known as a supercritical liquid. This liquid is under intense pressure. So in order to keep it as a liquid, it needs to be injected at least 2,700 feet below the Earth's surface. And so that's kind of the critical depth cutoff that we look at when we're assessing where potential storage sites could be. And so to dive a little deeper into enhanced oil recovery, as I mentioned, it's when you inject CO2 into an oil and gas reservoir. Now, there's oil and gas in the reservoir because the rocks are already permeable. They have open spaces. So that porosity and permeability is already there. The aspect of enhanced oil recovery that is somewhat beneficial is that the CO2 actually squeegees out or removes the remaining petroleum that can then be recovered and utilized on the back end. But again, we don't have any petroleum reservoirs in Iowa, so this is not something that would be at play here in Iowa. Really, the saline aquifer storage aspect is very similar to the enhanced oil recovery, except that instead of injecting into a porous rock formation that has petroleum, it's just a porous rock formation that has water. And so that's what an aquifer is. It's a bedrock formation that has open pore spaces where water can be held and transmitted. The issue with injecting into aquifers is the EPA regulates that any aquifer that is deemed suitable for storage of CO2 must be too mineralized to drink. It's, in other words, non-potable water. And the cutoff for that is 10,000 parts per million of total dissolved solids. Now that's really mineralized, salty water. It's essentially water you can chew. It would never be considered drinkable water. So that's one of the major parameters when looking at an aquifer for potential CO2 storage. We do have some of these in Iowa. And the last one I'm bringing up here is a little bit new to the game. Basaltic mineralization is being researched and deployed actually in Iceland under a company known as CarbFix. And what this is when you inject CO2 into bedrock formations that are made up of basalt or lava, the CO2 actually converts from the supercritical liquid into the mineral calcite or some variety of calcite mineral. So it takes it from a liquid and converts it to a solid. And this is something that I believe we do have a potential to do in Iowa, and I'll explain that later on. I really like showing this slide because it was one that I saw when I was at a conference earlier this year. And this was produced by the Department of Energy, their fossil energy and carbon management. And they run a program called Carbon Safe. Carbon Safe is the avenue in which the DOE provides funding for CCUS research. And this figure on the left is just sort of breaks down how they take a phased approach to providing funding via the Carbon Safe program. And it begins with the phase one, which is essentially a pre-feasibility, kind of a desktop survey using existing information to determine if there's a location or a site that's worthy of further research. Once you've determined that, then you move on to phase two, and that's where you're actually collecting new data, whether it's drilling or geophysical data or any combination of those things. And that's where you really start to identify if a site is suitable or not. Once that's completed, and if it's deemed successful, then you can move on to phase three, which is when you're actually doing injection testing, and then phase four, where you're actually building the infrastructure and deploying a commercial scale injection site. And with that, when the DOE presentation showed this table here on the right, where they mentioned that currently they stand at about 5 carbon safe projects that are being deployed right now. And in order to meet the United States climate goals for carbon neutrality, they see the need to upscale that from 5 to 600. And that gave me some optimism because I had been, over the last 3-4 years thinking about carbon sequestration. Where does Iowa fit in? I can't help but think that we've been really far behind the 8 ball on this. Some states neighboring us like Illinois and Kansas and North Dakota, they are so far ahead of us. I was starting to get a little bit discouraged, thinking, man, we're too far late to the game. But when I saw this, it made me realize I don't see how they can get upscale to 600 projects, that are commercial scale storage sites without incorporating Iowa to some degree. And, in addition to that, when you look at the amount of funding that has been provided, I can't remember what their initial budget was, but the bipartisan infrastructure law provided an additional 2.5 billion per year over a 5-year period. And so we're only 2 years into this. So they really see the need to increase the funding so that they can increase the scope and the spread of the research regarding CCUS. And I'd like to take a moment here to talk about some of the pipelines that have been obviously in the news, and I'll touch on this just briefly. But this Princeton study in 2020 identified where there are current CO2 pipelines, and you'll notice that there aren't any in Iowa or really in the Midwest. These are primarily focused in petroleum producing parts of the country, about 5,000 miles or so. But when they look at modeling out into the future where CO2 pipelines are going to be needed, they see, upscaling that from 5,000 to over 11,000 miles of pipeline. And I can tell you in almost every conference I've been to, talking about carbon sequestration, there seems to be just this accepted certainty that pipeline infrastructure is going to be absolutely needed to achieve our climate goals. And so if you accept that, then, they have to try and figure out, well, what's the most efficient way to get the CO2 from the sources to the sinks or to the storage sites. And again, this 2020 study shows a model where you can see in the pink lines in particular, starting in Iowa, going off to the Illinois basin, and then also going down into, the oil patch in Oklahoma, Texas, and others. So keep that in mind. That was what they had forecasted in 2020. But I want to move away from that and talk about, why does this matter to Iowa? And really, it starts with ethanol. Iowa is the leading state in ethanol production with over 4.5 billion gallons per year. And when I do the math, that equates to about 13 million metric tons of CO2 that's produced each year from the ethanol industry alone. The reason the ethanol industry is such a focus is because the CO2 that's produced from the fermentation process of ethanol production is nearly pure. And that's advantageous because you can just capture the CO2 without having to scrub it or treat it. And so that makes the process a little bit simpler. On this graph, when you look here on the right, it shows that ethanol is kind of in the middle of the pack in terms of industrial emissions across the United States. So it doesn't seem like it's going to get you the biggest bang for your buck, but I consider it sort of the low-hanging fruit because again, it's such pure CO2, and it seems like a great place to start. If I were to put coal-fired power plants on this graph, we would have to extend the scale out ×4 at least in order to capture the amount of CO2 that's produced from coal-fired power plants. I just like to throw that in there for a matter of scale and perspective. There was a really great publication produced in February of last year called the Atlas of Carbon and Hydrogen Hubs, put out by the Great Plains Institute, and they're based out of North Dakota. And the way they framed a lot of that publication was trying to identify, again, a relationship between the sources and the sinks. And the sources and sinks are identified in this map where the colored icons are the various sources. And then they have these sort of basins outlined. And you'll notice that the ethanol are the yellow icons. And of course, Iowa's got the vast majority of those. I'll outline Iowa here. But we don't really have a storage location, a sink or a basin, according to this map. And that's something that I would like to see modified if we can get additional research here in the state. The other thing I like about what the GPI publication produced was identifying existing pipeline networks. And that's something when I talk about this topic, I like to introduce to people just to let you know that pipelines are not a new thing, not in Iowa or anywhere else in the United States. And you can see where we fit here. We're crisscrossed by a number of petroleum pipelines, hydrocarbon pipelines. And then here, just natural gas alone, it's a veritable spider web here in Iowa. So again, pipelines are not a new thing. And just to let folks kind of get a visual on where existing pipelines are, in terms of our state. The other thing I'd like to add in, and I don't have a map for this, is that underground injection of things is not new to Iowa either. There are several places in Iowa where there are geologic formations deep underground where we actually pump natural gas and use the underground formations as like a storage tank, so that when natural gas is being produced, in the refineries to the south of us, they're constantly being pipelined up to Iowa. And in the summertime, when nobody has their furnaces going, they can store that resource for later usage in the wintertime when everybody's firing up their furnaces. And so that's just a really good example that I'd like to inform people about, is that we are currently doing underground storage of materials in Iowa. Now this model by GPI, a little bit different from the Princeton one, where it's showing a lot of the sort of idealized pipeline networks needing to take Iowa's CO2 south into the oil fields. And again, this would all be for enhanced oil recovery. So both of these models show, taking Iowa's CO2 and sending it somewhere else for storage outside of Iowa, and most likely for enhanced oil recovery. Well, it wasn't long after those models came out in 2021 when a number of pipelines were proposed for Iowa, and none of them followed the routes that were modeled before. So I kind of chuckle with that one. And this is obviously a rough map, but it gives you a generalized idea of where, we're familiar with the Summit pipeline that's aiming to take CO2 north and west of Iowa to North Dakota. And then the yellow or the orange is the Navigator pipeline going to the Illinois Basin. And then there's a small pipeline just connecting the ADM plant in Cedar Rapids to the ADM plant in Clinton, and then sending it to the ADM plant in Decatur, Illinois. So Iowa has over 50 biofuels facilities in the state, again, producing collectively about 13 million metric tons of CO2. If we were to find storage here in Iowa, would we need these lengthy pipelines? Could we get by with shorter pipelines or fewer pipelines altogether? And that's obviously a component of the research that I hope to see happen in Iowa to help us deal with the CO2 emissions that we produce here in Iowa. In talking about the benefits, the environmental benefits kind of speak for themselves, and I'm not going to address those here in detail. But really what we're talking about are the financial benefits and incentives for capturing carbon and trying to reduce the amount of CO2 that's emitted into the atmosphere. And it really starts with the federal tax program known as 45Q. I did some rough math here in the table on the right, and the numbers are different primarily because, again, with enhanced oil recovery, you're going to produce a revenue stream from the petroleum that is generated from the process of injecting the CO2. So the number of $60 a metric ton is lower than the $85 a metric ton because you've got that ancillary benefit of selling additional petroleum. Now, these two numbers were inflated or boosted by the Inflation Reduction Act of 2022. This number was previously $30 a metric ton for enhanced oil recovery and $50 for saline aquifer storage. So both of those numbers were increased, partly because they want to, again, stimulate the carbon capture part to help us achieve our climate goals. And when you take these numbers of 60 and 85 and multiply it by the amount of CO2 produced in total, so this would be if every single ethanol plant captured every ounce of CO2 under the 45Q tax credit program, that's an additional revenue of anywhere from 740-ish to over $1 billion of additional revenue to the ethanol industry in Iowa. And so this is where it actually matters. If the CO2 were to be transported somewhere else, is it going to be used for enhanced oil recovery, or is it going to be stored geologically in a saline aquifer? And this is what the difference is, and this is why it matters from the economic standpoint to the ethanol industry here in Iowa. But when I talk to folks in the ethanol industry, I consistently hear the message that the 45Q tax incentives are not the end-all be-all goal. Really, what they're looking at is being able to market their product as a low-carbon fuel. Now, there are 3 states in the United States, all on the West Coast, that already have a low-carbon fuel standard. And what that means is the carbon intensity score of that fuel must be to a certain point where they can identify it as a low-carbon fuel. Right now, Iowa ethanol does not meet those standards. If they were to capture their CO2, then Iowa ethanol becomes a low carbon fuel, and they can sell it at a premium to states that have adopted these standards. And I know right now it's just the West Coast, but there are a number of other states that are looking at enacting similar standards, and Congress has even been toying around with the idea of initiating a national low carbon fuel standard. So this provides the longer term financial benefit of capturing CO2 from Iowa ethanol plants. And lastly, I'll mention there is an even more localized financial benefit in the aspect of pore space leases. So to give you somewhat of an example, there are a number of underground mines in Iowa where limestone or other materials are being harvested from underground. And in a lot of cases, they're being harvested from under the property of private landowners. The companies that extract those materials from underneath private landowners, they have a lease agreement with the landowner, and the landowner gets a certain amount of money based on the material that's removed from their property. A similar type of setup could be done here in Iowa for injecting CO2 underneath private landowners' land. This is something that's been worked on at the legislative level in a variety of states, Indiana, Illinois, Nebraska, for example. And so this is yet another sort of financial benefit for carbon storage in Iowa. All right, now to my favorite part. We can talk geology. Where do we search? How do we identify if we can do this in Iowa, and where? So I want to start with this cross section. This is a graphical representation of the geology if you were to slice the state from northeast to southwest, almost like you're slicing through a birthday cake and seeing the layers of cake and frosting. And what you're seeing here in gray are bedrock formations that are mostly shales and things that don't allow groundwater to move through them. And then the blues are the formations like a sandstone or limestone where water can percolate through and flow. And those are our aquifers. And I've highlighted 2 of the lowermost aquifers that we have. There's the Jordan Aquifer and then the Mount Simon. And these aquifers are not quite deep enough throughout most of Iowa, but in the southwestern part of the state, they are below this 2,700-foot depth cutoff. So back in, it was about 2011, the Iowa Geological Survey did sort of a desktop survey of, where do we think that carbon sequestration would be most viable? And they were really focusing on the southwestern part of the state because of this aspect of these aquifers being deep enough. And so that report is out, and it's available for public consumption via our website, and it's a really great resource. And so looking at these aquifers, again, we have to identify, is the groundwater in these aquifers saline enough? And we really don't know the answer to that basic question, because we haven't drilled holes deep enough and taken discrete water samples from these aquifers to identify what the salinity is of those aquifers. So that's already an unknown. We do know that they are deep enough from existing wells, but we just don't have that groundwater chemistry data. We also don't know enough about the porosity and permeability of these units. So there's already those unknowns that we need to address. I like this little imagery just to kind of hammer home the idea of what is porosity and permeability. And so if this is a sandstone and these tannish brown are sand grains, the open space in between are known as pores. And so porosity is how much open space there is in the rock formation. Permeability has to do with how those pore spaces are connected. So you can have a rock that has a lot of pore space, but they may not be connected. So then fluids cannot necessarily flow freely through that material. And so in this case, if you were to inject CO2, you would actually depress the water and sort of push it out. And so that's one of the things that gets monitored in these types of saline aquifer storage sites. In Illinois, for example, they've been doing this since about 2007. And they have monitoring wells to monitor, is the CO2 escaping and leaking. They can also monitor the water pressure itself within the aquifer to make sure that it's not getting too high and generating other issues. But this little cartoon just kind of gives you a good idea of how the injection process might work at the aquifer scale. Now in Illinois, where they've done a ton of research on the Mount Simon in particular, they see porosity upwards of 25%. That means a quarter of the rock is open space. That's a very good aquifer. And it's deep enough, it's saline enough. That's why there's so much attention on the Illinois basin. And other places, that's an ideal scenario, but we don't know, again, what the porosity is of the aquifers we have in Iowa. The Mount Simon is in Iowa. It's the same rock formation that it is in Illinois, but it just happens to be deeper in Illinois. So, those are the things that we need to research. So really what I've been trying to talk about over the last several years is I can't help but think that this feature known as the Mid-Continent Rift System is probably our best bet for larger scale CO2 storage in Iowa. And on this cross section, the Mid-Continent Rift are these rock formations way deep down below all of the aquifers and all of the other rock formations that we're familiar with in Iowa. These are what we call Precambrian. These are very, very old, more than 1 billion years old. And they're almost entirely below this 2,700-foot cutoff on this particular cross section. There are no water wells in any of the Mid-Continent Rift rocks. And again, the majority of it is deep enough. So I think right there, this is worth taking a look at. So what is the Mid-Continent Rift? Well, a rift is where the Earth's crust actually is extended apart and actually tries to rip itself apart. If you can imagine South America and Africa, they used to be together and they have rifted apart and the Atlantic Ocean is in between. So that process almost happened here in Iowa. But since we don't have an ocean here in Iowa, that rift actually failed. For whatever reason, it was not a successful rift. But in the process of that crust thinning and opening up, it created fractures or fissures that were hundreds of miles long, and they were erupting lava, huge volumes of lava. And that's what the basalt is. In this map here, the central part of the rift in this greenish color is where all of that lava came pouring out. So we have basalts all down the center of the rift itself. And then on either side in the tan and yellow are basins that are upwards of 30,000 feet deep. And these basins are filled with things like sandstone, shale, and siltstone. So those are really good targets as well. Oh, I want to go back and point out that there was a really deep hole drilled in Carroll County, known as the Eichscheid hole, that was drilled by Amoco, and they were looking for petroleum back in 1987. This is a log showing you from the top down, and then down, and then down, and then down, and then down. This hole was 17,850 feet deep. Right at about 2,800 feet was when they ran into the Precambrian Mid-Continent Rift rocks. And from there on, for another 15,000 feet was nothing but what we call the red clastics. Again, these are sandstones, siltstones, and shales. So that right there sounds like a great target, right? However, one of the main reasons I think that the Mid-Continent Rift has not been getting a lot of attention is because the porosity and permeability that was identified in that one hole showed an average porosity of less than 6%. And remember, the porosity in the Mount Simon in Illinois was upwards of 25%. So this doesn't look very good, but you have to understand the data. And where this number of 1 to 6% porosity comes from was all way deep down in this well, 11,450 feet and deeper. And that's because this is a petroleum exploration hole. They were looking for rocks that would produce petroleum. And so these black shales are what they thought the source rocks were. So I believe that this one hole and these porosity measurements are not telling the whole story of the Mid-Continent Rift. And if you look a little bit further up in this hole where they didn't bother to take porosity and permeability measurements, here in this what's known as Unit H, we know that it's a coarse to very coarse, poorly cemented sandstone. So that already sounds like, lithologically speaking, that sounds like it's going to have a lot of porosity and permeability. It's something that we need to look at. And there are cap rocks above it, shales and siltstones that are above it that would create that seal that's needed for a storage structure. But I also think the basalts are a potential as well. And the reason being is, as I mentioned before, there is research showing that when you inject CO2 into basalt, the liquid CO2 converts to calcite. And there's this really cool image that I found from Washington State here in the United States in the northwestern part, where they have tested this theory already. What they did was a small scale study where they injected about 1,000 metric tons into a basalt formation. And within 18 months, more than 60% of the liquid CO2 had converted to calcite. And the rock itself has these holes in it that some of them were filled in with the mineral calcite. That's what this white stuff is. So it's a really exciting, research project that they did there. And there are others that are looking to scale this up to a larger scale to see really what is the storage capacity of basalt rock. So with that, and looking at the Mid-Continent Rift and knowing that Iowa has a huge, essentially unlimited volume of basalt very deep down underneath us, I see this as being a potential. So if you think it's got an unlimited volume, there's a potential that you don't need to inject it below 2,700 feet. It could be shallower. That's based on some of the research that's been done in Iceland, where they mix the CO2 with water and it absorbs and converts a lot quicker at shallower depths. And what I really like about it is it reduces the chances of leakage. So part of that depth issue and creating a seal over it is to make sure that that CO2 doesn't decompress and leak upwards and then get into aquifers or even escape back up into the atmosphere. But of course, more research is needed. And so, wrapping up where to search, I want to show you this map view of the Mid-Continent Rift. And this feature, again, consisting of the central basaltic region and then the red clastics basins on either side, in total, this underlies about 40% of the state of Iowa. And when I mapped the biofuels facilities, I could identify 57 of them. It turns out just over half of them are sitting on top of this feature in one way or another. And so that leaves us with essentially half of the ethanol plants in Iowa could potentially be storing locally. Again, that's without knowing the porosity permeability of the red clastics or whether the basalts that we have can actually absorb the CO2. But based on what we do know, there is potential here. So to sort of bring things to a close, how would we identify whether we can do this? It's essentially a phased process where we'd start by interpreting the existing data, which we've already kind of done that. Next is possibly doing a seismic survey where you actually use technology to image the deep subsurface without drilling a single hole. And that can give you really useful information about the different rock types that are deep down. Eventually, you would need to drill test holes and get actual rock samples that we could test in the lab. Also getting groundwater samples as well from a test hole. And all of that new data gets fed into computer models that can identify, are there any faults in the area? Is there potential hazards from existing wells that might penetrate your storage reservoir? Other structures and lithological variations and things. And these predictive models are really what helps drive the next phase of actually doing injection testing. And this is all folded into information that would be assessed by the Department of Energy and the EPA to identify if a site is worthy of further investigation. So, you know, as I mentioned, I've talked to legislators about this and other folks trying to you know, get attention raised and potentially even find a way to fund this research that the Iowa Geological Survey would love to do. We broke it out into two different funding models. One is looking at going after carbon safe grants, and that's something that we're actively trying to pursue. These involve, you know, 2 to 4 years of the grant funding process and collecting all of the information and trying to get to the answers that we need. If we had a more direct funding model, i.e. maybe the state of Iowa or the legislature, somebody wants to just give us funding that we could then use to investigate this, that timeline could be shrunk depending on the amount of money available and the questions that we're asking. So there's a variety of ways that we could approach this. Obviously, the more money we have, the quicker we can come up with answers, or the more sites we can characterize at a time. So in general, that's kind of wraps up you know, my presentation, and I want to leave you with an image of the drilling rig for the Amoco Eyeshide well. It was quite an endeavor back in 1987, and anyway, with that, I'll call it quits and open it up for questions. Oh, I see there's quite a few in there.
Yes, there is a few. It looks like a couple of them are relating to just kind of like the other things that go along with ethanol, like shouldn't we just be reducing ethanol more in general? And then if is the CO2 being captured, like the biogenic CO2, not really counting towards like a carbon intensity score? Would that, like how that maybe won't actually lower some of the negative effects that some people see from ethanol, and maybe if ethanol plants should be moving towards different like renewable energy sources, like for some of their processes?
Yeah, so what little I do know about the ethanol production industry is that they do have several CO2 emission streams. The biogenic or the fermentation process that's what generates the pure CO2. There is also a certain amount of fossil fuels that are being combusted to generate you know, the heat for boilers and things like that. So when I've talked to ethanol producers, just a few, they were, you know, able to sort of split those out for me and identify that they have, you know, the biogenic and then the combustion CO2. I don't know much about the actual capture science and process. That's a whole other industry that is going on. And so the capturing, I'm not sure if that's split apart, if they can only capture the biogenic versus the combustion, or if they can capture them both. But I know that there are power plants that are investigating this, and capturing from a power plant is very different from capturing from an ethanol plant. So I'm fairly certain that the capabilities are out there to capture any CO2 emitted, whether it's combustion or biogenic. So that's about all I know about that part of the process.
We also have some other questions. Like, have you looked at research about carbon sequestration potential of prairie restoration and compared that potential in Iowa to like CCS in Iowa, and kind of different alternatives or compared like ecological things with the co-benefits like bison and elk grazing. Have you looked into any of that?
As a bedrock geologist, no, I have not looked at all of those other options. I know that they're out there and all of them should be getting their due attention for sure. But being in the position that I'm in with the expertise that I have, I am focusing on the aspect of geologic storage and only geologic storage.
Okay, we have another question. What about the water consumption of carbon capture technology? The question references a report titled The Evaluation of Carbon Dioxide Capture Options from Ethanol Plants, developed by the Illinois State Geological Survey and the Midwest Geological Sequestration Consortium, released in 2022, provides field-tested numbers on water consumption. Based on the evaluation of ADM's CCS project indicator, these scientists report that every 1,000 tons of carbon dioxide captured daily requires 428 gallons of water per minute. Now, the Wolf Carbon proposal claims that it will capture 12 million tons of carbon dioxide per year. When you do the math, that's over 8 billion gallons of water consumed per year. That's just for capture and pressurization, not even putting the CO2 through a pipe. And the water would be taken from the Jordan Aquifer, precisely where like Lynn and Johnson counties, in a protected source area because of cones of depression detected in the aquifer. So why use some of the water, like the precious resource of water, on CCS?
Yeah, those are very good points, and those have been brought up to me in the past, because I understand that the DNR had a public meeting not too long ago addressing part of this aspect. And excuse me. What I do know is that the state of Iowa regulates the aquifers. They handle that. Certainly in regards to the Jordan Aquifer, being here in Iowa City, the Lynn Johnson County corridor is something that's monitored pretty extensively. And so, yeah, if that's the hurdle that we can't quite get over, or an ethanol, or a capture company can't quite get over because they can't find the water resources that they need to accomplish that, then that's just yet another hurdle. But again, I'm focused on how do we identify if we can do the storage here in Iowa. But from the capture standpoint, yeah, I know that there's so many other aspects that need to be factored into whether these activities are worthwhile or not.
Okay. Another question: will injected CO2 lead to aquifer acidification and potentially change the rock characteristics?
So that's a very good question, and I think there's no doubt that at some point over whatever period of time, could be tens or millions of years, that CO2 is going to eventually dissolve and mix with the groundwater that's there, and that's obviously going to change the chemistry of the water that will react with the rocks. I had not done the research to tell you exactly what happens, but that's certainly an aspect that needs to be considered. It's certainly for the nearer term. But that's a very good point, and I just haven't read up on the research on that aspect of it.
I know that there would be a number of variables to consider, for example, porosity and pressure, but how long would you expect a single injection site to function?
Yeah, the longevity of, and let's just picture a single injection well. And let's say that injection well is capable of taking 1 million metric tons per year. How many years can that keep up? Well, that's entirely dependent on the properties of the storage formation, whether it's basalt or sandstone. And those things get modeled in the beginning to decide if that's a viable storage location or not. And then from then on, it's continuously monitored, throughout the injection process, and then for a certain period of time post-injection as well. So again, this being somewhat new here in the Midwest, we don't have that long-term history to say we know what's going to happen. All we can do is model it up front monitor it during injection and then post-injection. But it's really dependent on the characteristics of the rock formations that you're storing.
And then what percent of Iowa ethanol plants slide directly over rift basalts or flank basins, allowing sequestration on site?
So based on the map that I showed earlier, and my ability to identify, I think it was 57 biofuels facilities, 29 of those 57, so just over half, are situated on top of some portion of the mid-continent rift, whether it's the basins or the central basalts. But it's right at half of the biofuels facilities, and that's not accounting for other emitters like other industrial emitters as well. I have not inventoried those, just focused on the biofuels facilities, but it looks like about half of them are situated on top of the rift.
CO2 can be used under CCUs for jet fuel, methanol, which can be converted into ethanol, furniture, etc. Have you investigated these as part of a renewed manufacturing plant process in Iowa?
That is outside of my wheelhouse.
In light of rejections to Summit's proposed project in both North Dakota and South Dakota, why are we as a state seemingly pushing for this potentially risky, unproven technology?
Yeah, I mean, saying that geologic storage of CO2 is unproven, I'm going to push back on that because we've been doing enhanced oil recovery since about the 1970s. That's why the earlier maps I showed in my talk, there are a lot of existing carbon pipelines in sort of the oil producing regions of the United States. And that's specifically because they've been doing geologic storage in terms of enhanced oil recovery since, again, about the 1970s. So we do have a really firm understanding of the process, the geologic formations that are needed to successfully store CO2 long term. So to address the question of why are we even looking at this, again, I'll point back to the carbon reduction goals that we've set collectively as a country. If we can capture CO2 before it's released into the atmosphere, I think we should. Of course, we should be changing some of the processes that emit the CO2, but it looks like this aspect can help us get to those climate goals a little bit quicker than trying to change some of these other processes that are responsible for emitting the CO2 in the first place. So in general, I guess I say if we can do it, if we can do something to help achieve our climate goals, then we ought to look at it.
For pursuing federal funding through Carbon Safe, could generating a partnership with ethanol plants in the Mid-Continent Rift area that we were committed to the now defunct plans for the Navigator pipeline help bring attention to Iowa and increase chances of funding for CO2 research?
The attention has been squarely on Iowa all along. Again, because we have the most ethanol plants, and the ethanol plants are sort of the low-hanging fruit. So, going back to the very first conference that I went to in 2019, it looked like Iowa was almost at the center of the bullseye. So, there's been a lot of attention on Iowa to begin with. With what's been going on with the pipelines, I can't say how that's going to affect what it is that I'm trying to do here with researching geologic storage. But what I will say is part of the reason that we haven't already done some of this and secured federal funding through the Carbon Safe program is simply because I'm the only person at the Iowa Geological Survey that works on this aspect. And so to go after a large federal grant like that takes a team of people a long time. And so we just haven't had the bandwidth to really go after one of these grants so far. But I'm excited to say that we're in the process of partnering with a variety of entities on submitting a carbon safe proposal in hopes that we can maybe get a grant to start doing some of this research here in Iowa. because this has already been done again in other states around us. And so, in that aspect, we're a little bit farther behind, but, we really hope to break into this here really soon.
Okay, and then this question is from Siri, who's a reporter with S&P Global. Why are Summit and Wolf Carbon pursuing geological storage in North Dakota and Illinois? Does it just boil down to the fact that those states' geologies have been studied more?
Absolutely right. I think you have to look at the history of the sort of the petroleum industry in those states, where to characterize and identify petroleum reserves, you have to do a lot of the same research that I'm talking about here in terms of carbon sequestration. So it's almost like petroleum geology in reverse. So the states that have had a history of petroleum production, they have a wealth of knowledge about their deep geology. Whereas here in Iowa, we don't have that history of petroleum exploration and production. So we're lacking that wealth of knowledge. So I really think that that's where it's the divide started, was those other states were positioned a lot better because of their history of deep geologic investigations for other industries. Whereas here in Iowa, we're a groundwater rich state. So, drilling for groundwater wells can be fairly simple, straightforward, and also fairly shallow. So I think, yeah, whoever asked that question was spot on. It's these other states have characterized their geology a lot better than we have so far.
Were the dollar figures identified at the end for a comprehensive statewide survey of all potentially usable formations, including porosity and permeability and impermeable caps?
No, those dollar figures are for essentially a single site. To put it in perspective, the Carbon Safe Phase 2 grant can be upwards of $10 million. And that's to characterize a single site. So a single ethanol plant or power plant. And that's because collecting seismic data is extremely expensive. The most expensive part is drilling the actual test hole. By the time you drill a hole 5,000 feet deep, you've retrieved several hundred feet of solid rock core, done all the analytical testing, done the downhole testing, which are geophysical things as well. Just drilling it and gathering data from the test hole itself can be upwards of $5 or $6 million. So no, those numbers that I showed are for really characterizing a single site. And then to characterize multiple sites, we would have to scale that up. So really, my hope is that if we can get a carbon safe grant to identify one site and that shows to be favorable, then maybe we can start building on that momentum and characterizing more sites simultaneously across the state.
Do you have any indication of the legislature's response to your presentation?
The response that we've had so far has been that they're very interested. They seem to be amenable to the idea of us doing this research and seeing if we can come up with other options to deal with the CO2 emission that we produce here in Iowa. So, but that's about as far as it's gotten so far. I haven't heard anything about trying to fund any of the research or anything like that yet. But I can safely say that our government is aware of this, and they know what you folks know now, and I'll just leave it at that.
How long did it take to drill the Ishide hole? I don't know if I said that right.
That's a really good question. I don't know exactly off the top of my head, but it would have taken, well over a month.
We hear a lot about permanent sequestration regarding CCS. That is when we aren't hearing about EOR. What does that mean in reality? How long? Who could be in charge of oversight on such an injection site? The federal government, the state, in light of ecological chaos right on by the land by the fracking boom, where we observe things like methane leaking into water sources, making them flammable and increased seismic activity. How do we know we won't have similar issues with CCS?
Right, all very good points. And I'll touch on the induced seismicity first. That's one of the things that the modeling helps bear out is, can we identify faults in the area, or other, structural features within the injection area. So the modeling, again, is built based on the seismic data if you've got it. Certainly the test hole data, that is very localized and very specific. So that is all formulated and constructed into the models to begin with, before the EPA or anybody even starts to think about allowing us to start injecting. So the EPA is really the main regulatory arm for any underground injection. You have to get, in this case, what's considered a Class 6 injection permit. And so once you've secured that Class 6 permit, you have to obviously satisfy the requirements of that permit in order to start injecting. And then as far as the ownership of the well, of the site, those are aspects that I'm not familiar with, but certainly have to be dealt with before, during, and after any injection takes place. You're still muted.
So sorry. Can the MG Eyeshide site #1 in Carroll County be used for anything in the future?
Well, the test hole itself has been plugged, so it's completely been filled up and capped, and it was in the middle of a farm field, so I'm assuming it's still a farm field today. So that particular well is not available. So, but we know a lot from that well, that we can propagate a certain distance away from that site, and then hopefully learn more from additional test drilling here in the future.
All right, so we are getting just to about 1. There's a few more questions still in the Q&A. Ryan, I don't know if you want to hang around, or if you want people to email you, reach out to you some other way.
I'm happy to keep answering questions if they're coming.
Okay, we'll do a few more then. Can you please address the following quotes? CCS is life support for the fossil fuel industry and a death sentence for the planet. This is from the Center for International Environmental Law. Carbon capture is being used as a Trojan horse by oil and gas executives to continue and even expand fossil fuel production. Environmental Defense Canada. It's simple. The world cannot meet its climate targets relying on carbon capture. The majority of CCS that exists is being used to extract more oil, ultimately driving more climate pollution. Global Witness. Once again, Black, Indigenous, and poor communities will be sacrificed just to ensure profit for polluting industries. We must reset our priorities to put people before profit. Gulf Coast Center for Law and Policy. Are you aware of real concerns being voiced by communities and organizations in Iowa about the effects of carbon capture on our state?
In terms of the overall, I guess, to overgeneralize it, should we even do carbon capture and storage at all? I've already stated sort of my position on that. I think if we can capture CO2 that's going to be emitted anyway, I think we should. My job here at the Iowa Geological Survey is to use my expertise to identify if there's a place that we can store that CO2 once it's been captured. So, I'll kind of leave it at that, because I'm able to sort of simplify it in those terms, that I think if we can capture the CO2 that's going to be emitted anyway, we should. I don't have an opinion to render here about whether we should be spending all of our efforts on trying to change, industries that are emitting anyway. But clearly the federal government sees fit to invest in trying to get this research in this industry off the ground and up and running, and they see it as part of the multitude of facets that are going to be employed to achieve our climate goals. So that's kind of how I see it.
Muted again, sorry. This is going to be the last question. So when comparing the capital needed to build pipelines or drill test wells, is one method less expensive? If you multiply the cost per well times the number of potential ethanol sites, how much money are we talking about?
That's an interesting question. I can't say that first of all, I'm not really familiar with how much it costs to build a certain length of pipeline. And even the numbers that I provided you for characterizing a site, those are very well-rounded numbers. So real gross estimates. I don't know that I could tell you, which one would be more cost effective versus the other. And even trying to equate the impacts of one versus the other. I mean, pipelines are at the surface, but they, extend along the surface. And so, is the surface area that impacts compared to, I guess the width of a plume, for example, if we want to consider that an area of impact. I don't know that I could speak to comparing those things in any reasonable manner. So yeah, sorry, it's just the financials I wish I didn't have to deal with at all. But I do, in terms of trying to fund the research that we feel is necessary to answer these questions. That part of the financials I do have to pay attention to.
Okay, that is all we have. Thank you, Ryan, very much for your presentation and for sticking around answering questions even a few minutes past time. The attendees who are still on, you and everyone else is going to get an evaluation email from me, so be on the lookout for that. And have a great day. Happy Tuesday, everyone.
Yeah, thank you so much for having me. I appreciate it.